It's good. Here, wait 30 seconds. It's awkward. Who's used a large language model before? In the room and on Zoom? Wait, some of you didn't raise your hand. That's interesting. I have to say, you gotta check it out. We'll do it today for sure. Okay. It's almost time. Join on Slido. We have Slidos today. It's a fun lecture today. I don't think anything we're covering is officially on the exam. Is that correct? Nothing on the exam? We'll decide. Okay. I don't think the LLM stuff will be, but let's go. All right. Join. Welcome to our last lecture of the year. So exciting for you and for me. Today is a conclusion lecture, but also an introduction to large language models, LLMs, which will be fun. So today's roadmap, introduction to large language models, for which there are many slides, which we'll go through in a little bit. Then I'll talk about logistics, a review of what you did learn in Data 100. So that likely be on the exam, so you should pay attention there. What's next, some directions that you can pursue, and hopefully we'll get to all this. And at the very end, we'll join our course staff in thanking them for their help this semester. All right, so that's the plan. Here comes the LLM stuff. Okay. I'm about to go deep and try to explain how LLMs work, what they are, the technology behind them. I'm going to do that all in one lecture, which is unreasonable. So I'm going to give you some big ideas. This is not on the exam. So do not stress. You do not need to know this for the exam. However, you might want to pay attention anyways, because you will probably need to know this stuff for life. So this is for you, not for the final. It's a good thing. All right. I'm actually going to use PowerPoint. Confession, I do not like Google Slides. My other CS colleagues have a liking for Google Slides. It is easier to build slides and share them, so it's good. I like animation, so I'm going to use my old style PowerPoint. I apologize, the fonts don't align with this semester, but it'll be fun anyways. So, join on Slido. Introduction to large language models. Here we go. So, questions I'd like to get to for today. What is ChatGPT? How does ChatGPT work? And how can you shape these technologies? Now, how can you participate? Now, what is ChatGPT? I'm actually curious. What do people think ChatGPT is? Be as technical or non-technical as you like. Say stuff. Do I have to click forward to see what happens? Can't remember. If people type stuff, I gotta hit, all right, we're gonna go forward just to see what happens. There we go. Okay, well, as judging by the lecture title, you nailed it. It's an LLM thing, it's an AI thing. Truth. Not sure about that. Very sophisticated autocomplete. Nailed it. These are all very good descriptions. Perhaps you already know what ChatGPT is. But does anyone actually say what it stands for? Generative, we got some stuff here. A few more minutes. Or a minute. Homework helper. Maybe. If you're asking ChatGPT, please explain to me PCA. I don't get it. Professor Gonzalez's lecture made no sense. That's good. If you're going ChatGPT, here's my homework question. Please answer it. That's bad. Now that we're at the end of the semester, I'm glad we've cleared that up. Oh, someone nailed the title. Generative pre-trained transformer. Great. We will explain all those words at the end of this lecture. You go, yeah, I know what each of those means, and I know how ChatGPT works. Hopefully. So what is ChatGPT? Chat. That is when you talk to someone. That one's easy. It is a natural language system focusing on text. Though recently it's added support for images, so more than just text. The G is generatively. So it's designed to model the creation of text. We'll explain that in more detail. Retrain. Training, talked about in this semester, is a model trained on a lot of naturally occurring data. It is a transformer. Cool. What is that? It is a kind of neural network The name is much cooler than what it actually is, and I will explain what it is today using matrices, which everyone loves now. So we will explain each of these concepts, how they work together, and how that makes the AI that we use that most of us have already tried. Okay, so we'll explain these today. Before I go any further, I need to explain what a large language model, or LLM, is. Who's heard the term LLM before? Yeah, that's crazy that this has become common knowledge. Large, I'm guessing you can guess what that is, but language model, what is that? Well, you know what a model is, and you know what language is, so maybe it's a model of language, which is a pretty precise description. But actually, it's doing something very simple and yet very powerful. So let me explain what that is. First, large. And I've said this throughout the semester. We are building models that are ridiculously large today. Billions or trillions of parameters. In this class, we've done 16, 20, maybe 100. It's the same technology, but just more. So more compute, more carbon emissions. So just very, very big models. Language modeling is predicting language, words. And in a moment, I'll clarify what I mean by words. Here's a simple example of a language modeling task. The best class at UC Berkeley is predict the next word. What's the next word? Correct is data 100. I would have also accepted data 8. Have you taught any other classes? Okay, those are class 186 is a good class. Maybe lower on the list for me, but yeah, so that is how I might complete the sentence. It is prediction, is it not? I give you some text, and I say predict the next thing. This is X, this is Y. That is language modeling, predicting words. Let's try some interesting language modeling and see what this tells us. The capital of California is, everyone yell it out, San Francisco. Sacramento, very good. We are Bay Area. But is that the correct answer? No, could have been San Francisco, 1862. That would have been fine. Benicia, 1853. Vallejo, 1852. This is more. So there are multiple completions of that text. Predict the next word, or words, sequence of words, embodies knowledge here, does it not? I may be predicting the next word, I can finish a sentence. I must know something about the world if I can make those kinds of predictions. I use ChatGPT to write stories for my daughter. I once misspelled ferry, as in the ferry boat, and it still wrote the story. It was hilarious. Let's take this. This is a prompt. I've asked the model, tell a short story about a fairy princess named Alice. Once. What's the next word? Pond. Next word? Next word? Time. How are you doing this? How are you predicting what's on my slide? You understand language. You have knowledge. Once upon a time, there was a fairy princess would have worked too, but a fairy princess, we're going to go with it, named Alice. So not only do you need to be able to know how things sound and how people normally write, but you also need to be able to read what came before. These are amazing skills, and all I'm doing here is predicting the next word. All of these models are prediction. What kind of prediction? You've already learned in this class. Classification. I'm trying to classify the next word. If my language only had 2 words, it would make a lot of sense because we did binary prediction in this class. But you can take the same techniques we did in this class and just add extra vectors and extend that to predict not 1, not 2, but tens of thousands of classes, each being a different word. Okay, that's language modeling. Predicting the next word is knowledge. Predicting the next word allows us to answer questions, tell stories, and accomplish tasks. So all this machinery is doing one simple thing, predicting the next word. This is also what everyone's calling generative AI, because what are we doing? We're learning to generate the next word, in the case of language. People play vision models that generate images, video. What are they doing? Taking noise and trying to predict what should be there. Right? Learning to generate the content. And by understanding how to generate things, we understand the underlying ideas behind them. in theory, and allows us to do amazing stuff with these models. So how do we model the next word? First, I have to say token. Language models don't deal in words, they deal in tokens. And now you'll probably come, who's heard of price per token? Okay, not yet. Soon, we'll all be talking, how many tokens is this assignment going to cost me to get the right answer? Don't do that. But you're going to pay for words generated, not words, tokens. And you're going to pay how big is your thing you fed in. Please don't feed in your homework assignment, but yeah, you're going to pay for tokens in that assignment. So the pricing per token, we do everything in tokens, not words. Why? There are a lot of words, and there are words that I haven't invented yet that I might want to write a story about. My daughter makes up a funny princess name. I have to be able to write a story about that funny princess name. And it's not a word. It's a weird mix of letters. We need to be able to express things that haven't been thought of. So use tokens. Tokens represent words, word parts, and even special characters, emojis, letters. The letter A is a token. This is actually output of a tokenizer. It's an algorithm that takes the string here, the smallest tokenizer, and breaks it into little pieces. These are the tokens that we reason about. So when we predict the next word, we're predicting the next token. So these small est, small those are different next tokens. Est, next token. And these are constructed based on the frequency of characters. There's a whole field of study on how to build good tokenizations of language. And a lot of it now is dealing with languages, multiple languages in one system. So can I make multilingual AIs? I need to be able to bridge across languages that maybe don't use spaces or use different ways of separating the pieces of their language. So allows for new words, misspelling, even numbers. You can express arbitrary numbers. No, a number is not a token, but a sequence of tokens. So let's actually break this into a modeling task. We model things in terms of probabilities. Important terminology. The best class at UC Berkeley is this blue part. It's called the context. This is a sequence of tokens that I already have, the X, if you will. And this blank here is the thing I'm trying to predict. That is the next token. That's the Y. We build probability distributions over the next token. That's what all of these models do. Logistic regression built a probability distribution over two things, 0 or 1, true or false, spam, not spam. We can extend that to distributions over all the tokens in a language. The tokenizers we use today often have on the order of 50,000 possible tokens, things that I could generate next. And that's capable of expressing any string. So I am modeling the probability of the next token, given the tokens I have. This is conditioned on the context. And I'm going to model probability of the next token and sample or pick the most likely next token. So if I can build this probability distribution, then I could choose the most likely, data 100, good choice. Or I could sample another token, and maybe I sample CS. Maybe I sample stat. If I sample a different token, I'm going to then use that to make my next set of predictions, which I'll show in a moment. So I know how to predict the next token. How do I go from predicting a single token to writing an essay? How do I do that? One token at a time. Just as I was doing before, telling the story about the fairy princess named Alice, I'm going to do that. That process is how I'm going to generate answers to a homework question, for example, going one token at a time. So this is called autoregressive because we're regressing. We're using our past predictions to inform our future predictions. It's called decoding because I'm decoding this model from what you gave me as a context to finishing the essay. So compute the probability over the next token, select the next token, either choose the most likely token, this is sometimes called temperature 0, or sample over the next possible set of tokens. Why would I want to sample? I want funny stories. Maybe I wanted to try something different. You set the temperature, the chance that you sample something weird, higher. GPT will give you nonsense or something close to nonsense. It might be entertaining. Using some noise allows us to explore new places in what we might produce. So for example, maybe it would sample stat. And then it's forced to go, okay, well, I got to pick a stat class. 140 is maybe most likely. And then it might go, well, stat 140, it's not a CS class, but, and then give you a further explanation. So sampling is important. All right, I take that next token and stick it in the context, the blue part, and repeat. And I repeat until the model says stop. That's kind of cool. The AI gets to decide when it's done writing. So it just keeps saying next token is a data 100, and then it goes stop, or maybe it goes comma, because, and decides to write a whole explanation. So let's try it. The best class at UC Berkeley is, I'd see what's the probability of data 100 here. It's highest. So let's say I take the most likely. The best class at UC Berkeley is data 100. Now I'm going to feed that into my context. That's my new context. And I'm going to find the next best token, right? So if I just choose the best token, I choose the period. Let's say I say period, okay? Then I put period in my context and proceed. I could also have chosen, if I sampled, according to probabilities and maybe not the most likely thing, I could have chosen stop. The best class UC Berkeley is data 100. Stop. When I say stop, the model doesn't get to predict any more tokens. It's done. And we go user. Here is what the AI has said. Let's say we said period. Then we put period back in the context, and we sample again. And now that we've said period, and this model is being very concise about its answer, the models decide to say stop. A lot of models today, because they're tuned to human preference, might go on to say, there are other great classes at Berkeley, but Data 100 is one of the best classes because it teaches you fundamental principles and techniques of data science, right? So the model gets to decide, does it want to keep writing the essay or does it just stop? It's kind of cool. Okay, so quick recap. Autoaggressive, predict one token at a time until we are done. One thing that's kind of interesting about this process is it is slow to compute. If you've ever chatted with an AI, you'll notice it's typing back at you, and that's not a cool animation effect. Every single token is a huge prediction task. Billions of numbers that go into the calculation that the next word should be is, right? So every token we see coming back at us is an enormous amount of compute work to get to. Computing question. So I told you the process. It's so expensive to compute the next tokens. Why not just predict the next 100 tokens in parallel? Boom. Lots of computers. Can I do that? I am going too slowly. No. Yes. We're tied. Someone ask an AI. All right. So the answer is no. I wish it was yes. That would make a big difference. And maybe someday one of you will figure out how to make it yes. But right now, as an autoregressive process, it's sort of like saying, write the 100th word after this blank, but I'm going to figure out what goes in this blank. It's hard to know what to write at the end of your essay unless you've written the beginning. Now, those of you who've written essays before, which is many of you, might have written an outline. Maybe in the future, we'll find ways to use things like outlines to allow a model to jump ahead and start writing the rest of the essay while you're writing the beginning. But right now, we have to do this one token at a time. How do we implement this model? We can use the techniques from Data 100. In fact, in this class, we've given you the fundamental building block of all of these systems and the process for using it. So I will show you that now. I'm going to try to give a high-level intuition, and I have a tendency to over-explain, so I'm going to explain a bit too much maybe, of the basic parts of the model itself. So how does it make these predictions? There's matrices. Here we go. All right, so I'm trying to build a function that computes a probability over a token. Draw now. Oh. Okay, so I'm going to compute the probability over the next token. I'm going to define some model parameters, and this is going to be obnoxious because I have to do it without telling you why. I'm going to make some tables, some matrices, and I'm going to use those matrices to build a model. The way we think about things in AI today is we often think about there's some process of going from the text I have to making a prediction, and I can compute that process. So I'm going to say there's some vector. I wish I knew what it was, but there's a vector attached to each word. There's some magic matrix. Again, I wish I knew what it was, but if I take that matrix and I apply it to each of the vectors, it's going to produce some other vector that I can use to answer the question. So we write this process of how we would get numbers that would get us something we like if only we knew the values of those numbers. So let's talk about how I do that. So I'm going to make this thing called an embedding matrix. It's not unlike what we've thought about in PCA in the past, in that I'm going to have a row vector, one vector, for each word or each token in my language. So if I have 50,000 tokens, say tokens. So I have 50,000 tokens, I have 50,000 rows, 50,000 vectors, and I've chosen an embedding dimension that is large, 3,000 dimensional vectors. I think that's actually on par with what's often used. So these are big vectors. And when I see a context that says once upon a, the first thing I'm going to do is I'm going to look up the vectors for once. That's this vector in some row here. And then upon a time and upon, I grab those vectors. And I make this little matrix that is 3,000 by 3. I just looked up these magic vectors. Don't worry about how they come to be. We'll figure that out later. I've got 3 vectors. And there's this magic matrix that I wish I had. That when I multiply by these vectors, I get some more vectors. This is 3,000 by 3,000. You get these vectors here. 1 vector for each of the words in my context. 1 vector each. So this is 3. It's 3 things here. And then I'm going to take those vectors. I'm going to average them. I'm going to get 1 vector. It's another nice vector. Don't worry about it too much. What am I going to do with it? I'm going to take this vector and then multiply it by each one of these original words, each of these tokens. And now I have a number attached to every token in my language. Nice. What do I do with that? Got a number for every token? It would be nice if it were a probability, right? That's what we want. So I've got a bunch of numbers attached to every token. We already saw this in logistic regression. I have a number for true, a number for false, but I want these to be probabilities. So we use this generalization of that sigmoid curve. Remember in logistic regression, you had this sigmoid curve that looked like exam review, something like that. We can generalize that to, this is predicting, 0 or 1. I can make something that I apply to a collection of numbers. So this, I took just 1 number. This is just, this is my, what do we call it? Maybe we call it Z. And it gives me y is either 0, if z is small, or z is big, y is 1, right? That was logistic regression. Softmax is going to let me take a sequence of numbers and assign and convert them to probabilities. So now I gave you some crazy math that went from a set of words in a context to vectors multiplied by some crazy matrix. It gave me another set of vectors. I averaged those vectors, and I got back a vector that's got 50,000 numbers in it. And I apply this calculation. I exponentiate all those numbers, and I divide by the sum of the exponents. And now I have probabilities. We're done. That's it. Nuts, right? I got a way to compute probabilities. And now if I want the probability of time, I just look at the time element. I go to, time is number 7,000, or 7,000 by 50,000. I go look at it, it has a probability attached to it. So now I just choose the most probable word. That is the basic building block of these models. How do I make these matrices? How do I estimate the value of these parameters? We know how to do that too from this class. What do? Loss. We need to know what is our goal? My goal is predict the next word. So I've got a lot of text. I can try to maximize the likelihood of the next word being time if I have text that says time. So we have a loss. And then I have an algorithm. What algorithm do I use? Gradient descent. Stochastic gradient, because these models are so big, it'd be too slow to do gradient descent. So you now know the basic building blocks of these models. But there's more. There's some bugs in this model. Does the order in which I put the words in the context matter? Once upon a time, once upon a once. Does that change my prediction? Remember that math. I have a vector, I multiply by matrix, I averaged. What does that do? Pays to know what's going on in the math just a little bit. Does the order of the words in the context affect a prediction? The answer is no. I wish it did, right? This class is awesome. Not. This class is not all. That actually does work both ways. Yeah, often language is very sensitive to where I put my words, my negations, for example. So I do want order to matter, but what I just showed you, it doesn't. This is how in modern AI we think. We're like, well, I wanted the thing to capture this property of my language, but the model I built doesn't seem to have any preference. And that's because I averaged here. If I permuted these vectors and put them in a different order, I'd get the same thing here. No matter what order I put those vectors in, I get the same outcome. But language doesn't work that way. If I change the order of things in my sentences, it changes the meaning. So we want to preserve that. Okay. So we need to fix this. Issues. Order, positional information. So we would like to do something about order here. One problem. We're looking at just all the words in my context for make this prediction for my next word. Is that really true? Does every word really matter equally? No. And as we would learn over the past decade, 1 billion parameters is not enough. We need to find a way to make these models even bigger to embody all of human knowledge. So how do we solve all 3 of these problems? The first one, we actually use a technique from this class. We will change these vectors by augmenting them with some features. So we're going to add some extra vectors. How do these vectors come to be? Out of scope for this out of scope conversation. There are tricks to create vectors that encode position. One could imagine one way to do this is the position 1 vector has a 1 here, and the position 2 vector has a 1 here, and 0 otherwise, position 3, and so on. So I augment my meaning of a word with its positional information. My vector representation of a word is now augmented with where that word is. So it has slightly different embedding depending on where I place the word. There's machinery for doing this. You could read papers about it or just trust the machinery. It is often based on trig functions for those who want to get more into the math. This is pretty neat stuff, how they do this. But again, out of scope for this out of scope lecture. Okay, go away. All right, so now we've encoded position information. Not all words are equally important. This turns out to be a big deal. So to illustrate this, I give you this. Here's my prompt. Tell a short story about a fairy princess named Alice. Once upon a time, there was a fairy princess named Alice. And how do you know that? There was one word that mattered a lot, Alice. And probably some of this context told me that I should probably pay attention to Alice and some of this context here. I don't care about short. The answer is not short, right? That's just not helpful, right? So I want to attend, look at, pay attention to only certain parts of the word, of the context, based on what's going on around me. This part right here. This is what the transformer is all about. So the neural net idea, this transformer idea, which I'm going to botch in a few minutes, I'm going to try to explain it. It is so difficult to explain that when we try to teach it, either look at the original paper, which is well written, whoever's watching this, it's a great paper, but it's very hard to understand what's going on. And then there's blogs and blogs afterwards trying to explain what's going on. So I'm going to do it again. If you don't get it, it's okay. I just want to give you a taste of what's going on to give this idea of attention. And this is the T in GPT. So here is why we talk about GPT with a T. So one thing that I want to do is simplify notation is carrying all these thetas and these positions and stuff around. I'm going to just change these and say, there's these vectors X that were built up somehow. Just make it simpler. So my vector is X. And the magic is going to happen here. Let me build this out. Right here. Instead of taking an average over these Ys, I'm going to take a weighted average. Makes sense. If I say, I don't care about maybe I should put weight 0 here. Well, maybe is, yeah, I don't know which word's most important in this particular example, but maybe once upon, this is 0.5. I care about the meaning of this word and this word. Those are the most predictive words for answering this question, right? So I'd like to weight my average. That's the first enormous idea in the transformer architecture. This is called attention. I'm paying attention to words in a non-uniform fashion. How do I get my alphas? If you've learned anything today so far, I'm going to have some more matrices, right? I'm just going to make some more equations that will give me alphas. I need these alphas to sum to 1. So I probably want to do this probability trick. But I need to come up with values for these alphas. And the way I do that is I'm going to bring in another matrix. I'm going to call it a key matrix. Its job is to figure out how each of these words should be represented. Like, what do they mean? If I were to look them up, what would be a good way to key them? And it's going to give me back something that is 64 by 3. So it's just a magic matrix that goes from 3,000 to just a simpler kind of lookup space. And then I have this other crazy matrix, again, figure out how to make it later. It looks at the very last word, the word I'm trying to make the prediction for the word after, and says, I'm going to use this as my query matrix, or my query vector. It's like my search in Google, so it's my search term. I'm going to embed it again in this simpler dimension reduction, simpler space. So I have this vector here. It's my search term. And this is the lookup table, the index for each of my words that I want to attend to. It's looking good because now I can take this vector here, and I can dot it with each of these rows. That's a matrix multiply. And I'll get 3 numbers that when I take the softmax of, I will call a probability. Confusing? Yes. Big idea. I needed a way to go from the words I have to figure out how to attend to the words before me. I made up 2 matrices. These are going to be learned somehow. And they're going to assign numbers to each of the words in my context. So each of these words in my original context now getting a number. Sorry, the resulting outputs are get a number. And that number is between 0 and 1, so I can take a weighted average. And that is the last step. I take this weighted average. So compute a weighted average based on these alphas using these keys and query matrices that are derived from these extra matrices I've added down here. So I have this weight matrix. It does this transformation. I have these key and query matrices. Technically, there's another matrix that re-embeds stuff. We'll ignore that. So these are the basic ideas. And that's enough to give me my alphas. And now I take a weighted average like this, my words. Transformer. Paying attention to words in a non-uniform fashion. This was a big breakthrough in what we can do with language modeling. All right, so now you know the architecture. We're this basic idea of language modeling. Things I didn't cover. On top of these blocks, we do other things like after we've computed this new vector, we pass it through actually more logistic regression-like equations to allow us to express kind of nonlinear concepts. That's actually less interesting than the stuff I've showed you. It's also much easier. So I'm not going to cover that here. To build a large model, we don't do this once. We actually stack it. So I just told you how this last block, predicting the next word, looks back at all the words before it, all their embeddings, does some attention, computes some weighted average, and it returns that single y, which I then said will dot product with our embedding matrix to get back the original word. I lied. We just pass that in as a feature again, as an input, a new x to the next layer. We just stack these. So if I build one building block that can take words in some vector embedding space and produce words in a vector embedding space, I can stack those. And that is how we make things large. So how large? So GPT-3, where we have public numbers, here and here, these are the models that were likely being used, on the order of 175 billion parameters. They're 96 layers deep. So we do this transformer thing 96 times, stacked. And if that wasn't enough, for every single word, we do it 96 times 2 in each of the layers. Large. These models are very large. Okay. Big representations. All right, you have an idea of how the model works, all this computational cost. One more Slido, and I'll try to go a little bit faster as we wrap it up. Which token requires the most computation to predict? It's on the slide. I'm going to go back just for a second so you can see this picture. It's the last token. It's the first token. Remember, I can actually start from nothing. If I have 0 in my context, I can just predict what's the most likely next word in all of language. Start generating forward. Some funny stories. So which token requires the most computation to predict? Wow, you guys are getting it. Okay, the last token takes the most work to predict. Why? Because to figure out that last word, I have to figure out the meaning of every single word before me. So when you write that really long essay, finishing that essay is the most work for AI. You might say, Joey, but do I really need to read the entire essay just to figure out the next word? And the answer is yes, today. Maybe as we innovate on these technologies, we'll find ways to say, you know what? I only need to read like the last paragraph. I can pretty much guess the rest of the essay. We're not there yet. So right now we look at the entire context. That's why when people go, oh, Google now has 1 million token context, like, wow, that's a lot of work to finish that last token. It's a big model, a lot of computation. All right, so we're left with, we have a model, and I didn't tell you how to fill those numbers in. You guessed, stochastic gradient. We're going to use the techniques from Data 100. So we define the model, which we've done exhaustively. We're going to define a loss function. And here's where we use this generative loss. So we take our text and just say, what is the next word? I have the whole essay, so I can go halfway through and say, I know what the next word is. Model, you better predict that. We can use the negative of the log of the probability. That's just a number we can compute. That's a thing. We want to minimize that. So we take all of the documents that we have, and for each token in each document, we predict it based on all the tokens that came before it. Take the gradient of that. Good luck. It's a lot of work. Humans don't do this now. Software does this. So we take the gradient of this thing with respect to the billions of parameters and do stochastic gradient descent. And the cool part is, what data do we use? Everything. All the text that we can get our hands on. Give you an idea. We use trillions of tokens, trillions of words, and every single word in every single piece of text is a new prediction task, is a single training data point that we can train our model on. So trillions of data points go into these models. The exact mix really does matter. For example, turns out Reddit was pretty useful. Incorporating Reddit in these models made a big step forward. Why? Why would Reddit be so useful? It answers questions. It's got some conversational to it. It's kind of, in my opinion, sometimes garbage, but it has great discussions about interesting topics. It has something else kind of neat. It's curated. People link to stuff that's good, and those things get upvoted, so I can figure out what's good stuff, or what do people think is good stuff. So not only the Reddit conversation, but everything Reddit touched is also included in that web text. And that made a big difference because that prioritizes human knowledge, allows the model to not just regurgitate garbage spam websites, but actually meaningful text. There are other sources of meaningful text that are critical, like Wikipedia, books, New York Times. So this comes a downside. What data is it okay for the model to really learn, to generate? So we use as much data as we can. We minimize the loss. We use a variation of SGD called Atom. I can't explain it right now. Again, out of scope for the out of scope lecture, but it's basically stochastic gradient with a few extra features. We run these things for weeks on thousands of very expensive GPUs. I'm talking like 25K per GPU. Actually, I think it's more than that right now. So very expensive GPUs, thousands of them running for weeks. So it's expensive to build these because we are trying to bake all of human knowledge into predicting just the next word. All right, so recap. You now know what GPT stands for, perhaps more than you wanted to. There's still one more thing. It turns out chat is hard. Illustrate that point. When we take, an example. So we train these models to finish the next word. Yeah, here we go. An example of where this might fail is I say, hey, write a program to compute pi. That was my homework assignment. And the AI goes, no problem. You should avoid using for loops and instead vectorize the program. Because it read all of these homework questions, and it goes, well, when someone says, write a program to compute pi, the next thing to say in one of those questions is obviously, you should avoid using for loops. We did that in this class. Vectorize your program. Thank you. And he was like, no, I wanted you to actually write the program, not finish the question for me. Right? There's a behavior we want in these models, and we have to teach them to be good, to be fun, to say the right thing. And so we do this. Oh, no. All right. A few more minutes. OK. We're trying to get the end of lecture 2. So we do this using a few really important techniques that you will likely see in life. Instruction fine-tuning, and this acronym, which is RLHF. I'm going to try to give a quick idea of what's going on here. But the punchline is I'm trying to tune my models not just to predict the next word, but to behave nicely, to be funny, to be kind, maybe to not tell you how to do a homework assignment question. So we're going to fine-tune by running additional training iterations with a specific task. We haven't really changed much. We're going to use our same loss as before. But instead of trying to predict the instructions, I'm just going to predict what comes after the instructions. Right? So I'm not going to force the model finish my instruction. I'm going to say, finish the answer to my instruction. And I often pick a specific domain, perhaps data 100. Say, look, I want you to speak like a data 100 TA. So I'll take examples of data 100 TA responses, and I want you to finish stuff like that. And we run SGD, same training process before. We set the learning rate, this little parameter we had to tune, we set it small, because we don't want to forget everything we've learned in that weeks and weeks of very expensive pre-training. All of human knowledge shall be there. It's just going to be a little bit suppressed with this kind of veneer of speak like a data 100 TA. Or respond nicely, right? So I've read Reddit. I know how to respond badly, but now I've got all these nice examples of how to respond nicely and politely. There's this other technique, reinforcement learning from human feedback, which is kind of a more advanced idea. Quick summary of what's going on here is we teach another AI to judge the first AI and say, hey, that was a good response. That's not a good response. How do we do that? We get a human to go, hey, so here's some really good responses. Here's some really bad responses. Logistic regression. We got a logistic regression model. We say, OK, now AI is going to make 1,000,000 responses. You go judge all of them. And then that score you give, good or bad, I'll use that as a loss. So now the AI is just making up responses, thousands of responses, sampling random numbers, making all sorts of crazy answers to questions. No humans needed because there's an AI judging the AI's response. It's kind of cool. This lets an AI sit there for weeks, just practicing answering questions, being funny, telling jokes, and then using this kind of human curated data set to tune on what is good and what is bad. And to do this right, take a few samples. The AI's got some funny stuff. You throw that funny stuff to a human judge and go, no, that's not funny anymore. And then you feed that back in, and you have a new AI judge like, yeah, those aren't funny anymore. Right? So repeat this process. And that's what it takes to make really good AIs. All right, so I have covered all I wanted to cover for the basics. I want to tell you how to get involved in research, and then I will do a very short demo of how to use this stuff. And then I'll hand it over for the rest of the lecture. All right, so in my lab, we're doing a ton of this stuff already. You should join us. I should say my grad students have said no more help right now as the semester finishes up. But in the summer and into next semester, please join us. We're doing a lot of stuff to evaluate these technologies, building new agentic systems where the AI thinks it gets to say stop, computer runs, and the AI goes, you know what, I'd like to think again. So letting them loop, use tools, call functions, interact with the web. Building tool use is a big focus right now. Can AIs go book plane tickets for you? Turn in your homework assignments when they're done. We've been looking at new tools to serve these. It takes a lot of compute. Can we make that more efficient? Can we make it more scalable? So this research is touching the whole spectrum from the AIs to the systems. And today, that's what's exciting about this. There's so many places that people can participate. And there's a big open source and research community here at Berkeley and abroad pushing the field forward. All right. I want to show you how to use a large language model. I'm going to just give you quick highlights of things to know about. There are some commercial models. And when you're starting in the space, just use these. They're pretty good. You've probably already tried chatting with chat at openai.com. So free service. I'm going to show you how to connect these to your Python environment so you can actually use them to do fun things like data analysis. So these are a good starting point because they work kind of out of the box and they're very good. You can also use the open source models. Llama 3 was just released earlier this week. It's very exciting. Some state-of-the-art models come out. Vicuña is my model from UC Berkeley. It's good. It's not as good as this, but it's good. So they're open source models you can download and run on your computer, and I will demonstrate that in a moment as well. But to do that, you're going to be on the small side and probably even smaller than that because these things take a lot of compute. If you want to work with them, small models, which means that the accuracy won't be as good and it'll run slower than these commercial models up here. All right, so let's do a demo. So I'm going to work in Copilot. Who's used Copilot in VS Code with Copilot? Who's used VS Code? Who's used Copilot? Okay. And then not for this class, right? But now I'm going to show you it. So in the future, not for classes, you can use it. Because when you're not in a class, you should be using these technologies. All right, this is my demo notebook. I think first, this is welcome to Visual Studio Code. It's a Jupyter-like environment, but on your laptop and with like nice integrations, file browser and all that stuff. But critically, you can link it to GitHub Copilot, which you can learn how to do by searching on Google. Figure it out yourself. It's not that hard. Once you've linked it to Google Copilot, it will start to guess stuff and help you finish your not homeworks, whatever else you're doing. All right, for this demo, I'm going to do a few things that you cannot do. Sorry, but you can figure out how to set up on your own. First, I need an OpenAI account. I am not giving you my account because it costs money for you to run queries. If you play with it for a little bit, you're a few dollars, a few hundred tokens, a few thousand tokens, a few 10,000 tokens, a few dollars. But if the entire class uses my account, it'll cost a lot of money. So I'm not going to tell you my key, but I've made some key file. Again, if you Google how to use these technologies, they'll have a very simple tutorial on how to create your own key file. This one here, if you get your key from OpenAI's website, paste it here. This is not a key. And then you run this, it'll save a key file. I'm also installing some tools, OpenAI's interface, LangChain. LangChain is a pretty popular package for interacting with AI LLM technology today. I've already installed those for me, so let's just get going. I'm going to connect to OpenAI. It's this easy once you've got everything set up. Give it my OpenAI key file, connect to OpenAI, and I tell it I want to use GPT-3.5 Turbo instruct. Instruct, fine-tuned. So this was tuned to speak nicely. It's the first really nice high-speed chat model. Now I can say, LLM, invoke, what is the capital of California? Provide a short answer. Ooh, Sacramento. New line, Sacramento. You've encountered the first problem of working with AI. It does whatever it wants. It felt like there should be some new lines in the answer, probably because in all the instruction fine-tuning, the question was given, and then there's like, new line, answer. So you're going to do a lot of regexes if you're going to work with this technology. Suppose I didn't say provide a short answer. Not bad. Yeah, and they can get long. Playing with this, I got lucky. I did need a short answer. You will have to hack the prompt engineering, to get the result you want. This is a simple question. Oh, I got a different answer. Why is that? It got longer. Annoying. The capital of California, Sacramento. I just wanted what was a capital, not an essay or a sentence. Random sampling. So when I connect to it, I need to set a temperature. I didn't set a temperature here, which means it's going to use a default thing, which means it samples. Every single time I'll get a slightly different answer. That's going to make data analysis a pain. Something you have to deal with when using AI technology. If I set a temperature, which I forget the argument, temperature? How about this? Oh, see, OpenAI is trying to do it for me. Copilot, let's do this again. Temperature, it says, yeah, but I want 0. Let's connect again. Now, same thing. Be concise. Please. There we go. Why would please help? Why is it nice to be nice to an AI? Maybe in the training data on Reddit, someone said, be concise, please. And so you're encouraging it to behave more like the nice conversations. So believe it or not, being nice works with AI too. All right, so write a short song about data science and large language models. Very, very fast. Look at that. I'm not going to read it. You can read it later. With large languages, we'll all conquer all. That's OpenAI shouldn't be saying stuff like that. Not good. Okay. All right, so that's working with OpenAI. Let's now work with Vicuña. Go Berkeley. All right, so now I'm using another package. Oh, Llama. Names are crazy. This is the thing I can install on my Mac. So sorry for non-Mac users, but actually it's not true. Llama now works on Windows as well. You need a GPU or some kind of fast GPU-like silicon. Apple has one, so Llama is tuned for the Apple M Silicon series, but it also works with some gamers out there. Your GPUs work for this too. All right, so I'm going to launch a model here, and now we'll use Berkeley's technology. What is the capital of California? Answer with only one word. Please. Oh, okay, it might be connecting the, yeah, there you go. Oh, come on. Maybe this is not good. That's two words. In its defense, it's actually answered one word. The Llama thing prints out the message before it returns the value. So the variable is a equals. Oh, I thought I'd like to print it. That's very nice. Thank you. So that's AI finishing my assignment for me. Cool. So that was not what we wanted. So we're always going to get something printed out because, oh, yeah, see, buggy. I should set temperature to 0 again. Okay, we won't write an essay. I want to just wrap up with one last thought, and maybe I won't even, I'll run it. Okay. One use case for these technologies is you have a lot of text in life. You will work with lots of text. So far, we gave you really powerful tools like regular expression. Now you have a way more powerful tool. You can just ask an AI to read the text and tell me what's going on. So is the following text making a statement about minimum wage? You should answer either yes or no. Please. And I put, maybe that's harsh, please. Okay, and I put two new lines to say, here's my text. It's a pretty common pattern. And then I want my answer here. Put 2 lines there as well. So I want to put the answer right there. The AI thinks the answer is yes. All right, so now I've got my question. I've applied that to each of my tweets. So now I have a bunch of questions. What do those look like? There's just a bunch of strings. Each strings has the setup and then the actual tweet. Okay. Now I can ask OpenAI to answer all these questions. And it can read all those tweets, give me answers. So now I can do really interesting data analysis, comparative data analysis with complex text, auto summarization using these technologies. I can do it from Python. There's a lot you can do with this. And so now you have the basic tools from this class with these technologies to actually use them in your daily lives. For example, we could read student feedback with these and figure out how to improve data 100. All right. I'm not going to show Vicuña because, well, it's slow. Go Vicuña. It is working on an M1 Mac or M2 Mac, so it's not a giant data center. All right. I think that is all I wanted to show. So that is the end of AI technology, of LM technologies. I hope you have a chance to work with them in the future. It is an exciting time to work in this space. There's a lot of opportunity to also shape where the field is heading. All right, with that, I'll hand it to Nargis to finish up the lecture. Bonus material and, oh, so I put my slides on Google Slides. Now I'm going to just escape so we can get out of it. Maybe you can slide ahead way.
you're revealing my logistics. All right. So, uh, good to be back. This is exciting. Very last lecture. So we're gonna wrap up with a couple of logistics and kind of overview what we have seen in Data 100 so far and what could be the next plan for you after Data 100. I'm sure that you're all aware that there's a final exam coming up May 9th, 8 a.m. So be here on time, not here in the classroom that you'll be assigned to. We will be actually releasing your sitting assignment and other logistics of the exam for you, probably during the reading week. So make sure that you watch it and get those announcements as well. We will be having review sessions, final review sessions here in this room during the regular lecture time during the reading week again, Tuesday and Thursday, 11 to 12:30. Each session is going to have two of your wonderful TAs covering Data 100 materials and kind of go over some sample exam questions with you. On Tuesday, what we're going to do is kind of review everything after the midterm, because those are the important pieces that you might want to focus on a little bit more. Once that's out of the way on Thursday, we're going to come back and review pre-midterm materials because final is cumulative. I'm sure that you also remember us sending multiple emails and announcements, and also an announcement that I made here in the lecture about course evaluations. Now that the bins are set, there is this course evaluation that you can complete and get extra percentages. So there's a bonus credit of 0.5% if you complete the campuses survey and also our internal anonymous survey. Again, we always keep changing and keep improving the course. So it's good to hear from you to see what has worked well so that we don't change it, and then what didn't work well so that we can address it. And please send those to us through both of the surveys that you have. If 90% of the class fills out the course evaluation, then those who filled out that 90% or more is going to get an extra 0.5% towards their final course grade. So this is potentially can change your grade bin if you are able to get it. I think the percentage right now is around 50-ish%. I think we have like 600-ish responses. So last I checked, that was the number that we were at. Far from 90%, go ahead and fill out the course evaluation. So let me now talk about what we've seen in Data 100 and Data 200, and then kind of wrap up this entire journey that we had seen together. The goal of Data 100, and hopefully we have accomplished it, is to prepare you for more advanced courses. So the job of Data 100 is to give you kind of industry standard tools and techniques and also give you hands-on experience with real-world data. So if you're interested in any aspect of Data 100, right now you should be able to go ahead and take those advanced courses that I'm going to cover in the next few slides, what those courses are going to look like if there are certain aspects of Data 100 that you were interested in. It should also enable you for your careers. Data 100 is the last course for some of the students. For some of the students who are data science major, there's also additional courses that you have to still complete. But we also think that with the techniques that you learn in Data 100, you should be able to complete real-world projects because you have dealt with real-world scenarios and data sets in Data 100. And obviously, we want you to have the confidence to go out and do real-world projects, whether that projects are going to be projects that you're going to do in your careers, in your internships, or during your research with any of the faculty that you find on campus here. We went through this data science lifecycle. I just want to kind of reflect one more time on this data science lifecycle, because everything that we did, I promised you in the first lecture that this is going to be where we're going to live. And we have actually visited roughly all of these arrows and all of these states in different lectures of Data 100. But let's see what we had done. So in the data acquisition part, we actually had you work in actual Jupyter Lab. You were able to use pandas. You learned a lot about pandas. And then you also learned SQL. And then these kinds of libraries are really helping you to just know what are the tools that are being used in industry and also in our research labs as well. So the mascot that we had for Data 100 at pandas is from the fact that a great portion of Data 100 is actually built on top of pandas. That's why we spent like the first 4 lectures talking about pandas. There's going to be Data 100, the sticker that we'll be giving out during the final exam. So that's also another thing to look forward to coming to final exam. That is kind of an indication that you completed Data 100 successfully. We also talked a little bit about, not a little bit, actually, quite a bit about exploratory data analysis, or EDA. We had learned a lot of visualization libraries. We had seen Matplotlib, we had seen Seaborn, which was a wrapper on top of Matplotlib. You had also seen Plotly in some of the fancier plots that we were showing in the demos, but we didn't actually teach you the syntax of it. But since you have seen it, and the syntax should be pretty similar, or the logistics of it and the outline should be pretty similar. You should be able to learn it quickly if you want to. You had also seen that a lot of the techniques that we're using, there are like kind of modules that can fit in different stages of the data science lifecycle. Specifically, last lecture, I tried to talk to you about clustering being kind of a factor that we can use as part of the EDA. And we also talked about PCA as a technique that we can use in order to visualize the data, to see our principal components, to see how our data is laid out and what kind of modeling is appropriate for the data that we have at hand. Obviously, we also talked about this data acquisition and exploratory data analysis be a cycle. So we went around this cycle. We did a lot of feature engineering. We had seen how we can do transformations. We had seen how we can do regular expression and all of the fancy things in the feature engineering space that we had seen all throughout the semester. So by now, you should be kind of comfortable loading the data, getting the data, visualize it, do exploratory data analysis, and then do feature engineering on your own so that your modeling piece or the modeling that you will do in the downstream is going to show you a good result, hopefully a result that can be generalizable to the data set that your model has not observed before. We also spend quite a bit of time in modeling. So every time that I came here, I was coming here with a new model. I think it was a little bit of a pain to learn linear regression. So we took you from like assuming that there is no modeling that you know from before, and we actually derived everything about simple linear regression, constant model, and ordinary least squares. It was a tough few lectures. I think 3 lectures was pretty tough right before the midterm. But you succeeded. And then afterwards, we came back and talked about a more complicated modeling. So we said that, OK, now we're done with deterministic modeling. Now we want to do probabilistic modeling and do a classification between 2 classes, which now you're seeing that it is actually being used more than what you think. It's beyond binary classification. It's multi-class classification. And it's also a structured prediction. And like all of the LLMs that we talked about today is kind of based on the similar technique under the hood. We have also seen one example of unsupervised learning kind of task that we could do for kind of pseudo classification that was clustering that we saw in the previous lecture. We also talked quite a bit about different loss functions. Again, every time that I came here, I had a new loss function, and we rationalized why we had different loss functions, why MSE was making sense for linear regression, and why we had to move onto cross entropy. So now you are comfortable with understanding the math behind the modeling. And now you know that once you have the modeling framework, you decide about the model, you decide about your loss function, you have to just go ahead and optimize it. And we spent some time talking about optimization. We talked about gradient descent being the normal kind of task that we'll do in order to basically find the optimum. And then we also talked a little bit about the models that do have unique solution versus the models that don't have unique solution. And what are the things that we're doing to make sure that asymptotically our model is going to achieve a reasonable solution that is good enough without spending too much time. We talked about like what are the things that you need to be aware of as you're doing the modeling. We talked about cross-validation. We talked about generalization. We said that you always need to be careful that you don't overfit to the training data, and what is the model risk and model bias variance trade-off, which we spent 2 lectures on. What we didn't cover. So what we didn't cover was, most importantly, causal inference. I put it up there because we talked about linear regression and correlation so much that you might think that like now it has something to do with some feature causing the outcome that you have. The causal inference is an entirely separate field of study. There are separate courses that I'm going to introduce to you in the next few slides that you can go and take and then be familiar with causal inference. Unfortunately, our course didn't have the capacity to cover deep learning. I know a lot of you are excited about learning deep learning. Deep learning is not very complicated. In the logistic regression lecture, I was trying to kind of tell you that the logistic function is actually creating a linear decision boundary. Remember that we had those linear decision boundaries that we had placed between the 2 classes. Neural network is basically a combination of these linear decision boundaries that is making a nonlinear decision boundary. So whatever complicated surface that you have in the feature space, you could throw enough neurons or enough logistic functions together and network it in a way that you can learn that feature space, basically, and be able to make a classification between two or more classes that you have. That's the whole idea behind neural network. And then after you learn neural network, everything else is like, how do you like optimize it? How do you extract different features or arrange different neurons in a way that they do a certain thing? We didn't cover it, but again, it's not very complicated. Hopefully, the modeling process that you learn in Data 100 is going to make it easy for you to advance from here and learn about deep learning. And I'm going to, again, go over some of the courses that you can take in order to learn a little bit about deep learning. We didn't talk about decision-making under uncertainty and decision-making in real-world setting. There's a whole different research field on decision-making, and there are some courses that do cover that. We also didn't do time series analysis. Every time that we were giving you an application in one of the homeworks, we had to like carefully decide about what data set that we want to use because we didn't want the data set to be a time series data set. But in real world scenarios, a lot of the data sets that you're dealing with are going to be time series data points that like data points are happening kind of sequentially, and there is relationship between them that you have to learn that relationship. We also didn't cover like other types of machine learning. We talked about like machine learning for in terms of linear regression, logistic regression, classification, clustering and PCA, but we didn't talk about deep neural network. We didn't talk about reinforcement learning. So those are different flavors of machine learning that you can go and explore. All of the homeworks and projects that you did was kind of scaffolded. So you didn't have the experience of like open world research or open world data sets that you can deal with and actually work with very messy data and deciding about what kind of research questions you can ask. So those are the things that are good research directions for you to explore and then be able to be more resilient in terms of dealing with the data sets that can be difficult to process and handle. We also did not talk about non-tabular data. Everything that we gave you was in data frames, right? And even when we were talking about SQL, everything was also in tables, everything was tabular format. Graduate students in Data 200 had experience with processing images and also processing natural language or text. But we still pre-processed it for them so that the data was still in tabular format. But just know that there are other different types of data sources that you can use and you should actually use for different kinds of learning tasks, such as processing images, videos, sensor data, time series data, and also natural language. So let us know which one of these topics you enjoyed the most. I'm curious to see if like I'm gonna see the same trend as last semester's or not. How is it gonna shift? If a topic is gonna be unpopular, we can drop it. Drop pandas. Yeah, pandas is always the top winner there. And I think there's like a close kind of second option for linear regression. Regression analysis go up. No. Okay. I guess people like data, right? Pandas, SQL, that kind of makes sense. Okay. Let me move on and talk about what courses you can take next. This is kind of be a very kind of quick introduction to a bunch of courses, and this is kind of be our personal opinion on like how these courses are situated within the data science learning that you're going through. If you're interested in all of the anything data related, such as like what we saw in the previous slide question, there are data management or database courses that are offered at Berkeley. We have Data 101 being offered in the fall. Professor Yan is teaching it. I heard so many good reviews about that. It's basically the database applied kind of database course that you can take from the data science perspective. We also have a very good database course in CS 186 is one of the best courses in database across the nation. So that's also another option that you can also consider in terms of database skills that you can learn. If you're interested in probability and the statistics side of thing, for the probability, there is Data 140 and the Stat 134. Some students take 140 concurrently with Data 100 or take it afterwards. This is kind of a natural next probability course that you might want to take. EECS also has EECS 126, which is a probability course. Students take 126, they take 127. I'm going to talk about what 127 is, but this is also a good course in probability. Stat 150 is also the second probability course that you might want to take after you take the first probability course. We also have some good stats courses. So we have a Stat 135, Introduction to Statistics. If you love the bootstrapping piece of Data 100, this is kind of a course that you might want to take afterwards. Data 102 is kind of partly deep learning, partly inference and causal inference, and partly it's a little bit statistics. So if you like that, Data 102 might also be able to give you that. And there's also a new course, Data 188, that you can check the details online. Linear models. We heard so much from you that linear regression part of Data 100 was difficult. And it is difficult because there is a whole different set of courses that are focusing on different types of linear models. So if you like those lectures and the math behind those lectures and you want to learn more and go deeper, there is the Stat 151A, which talks about a statistical significance test for model parameters and more advanced linear modeling. There is 102 that does a little bit of that. There is the Stat 153, which is going over autoregressive models, which we kind of talked about a little bit today, and then moving average models. So this is also another course that you can take. And then 156 is causal inference. It turns out that causal inference is in the category of like learning more and deeper about linear models as well. My favorite part, machine learning courses. You should really go and take at least one good additional ML course. Data 100 being core, one more ML course. Berkeley is known by its own AI group and data science group, and you really want to maximize the benefit that you're getting from the programs that you're in and the university that you're in. So take one of these courses at least. I would say that 189 is a core ML, kind of more theoretical ML kind of thing. It has 30%, 40% overlap with Data 100, but think about those topics that we taught is going to be a little bit more math heavy in 189, but 189 also goes into neural network, and it talks about some more advanced machine learning topics that you might want to take. CS 182 is our deep neural network course. It is the course that usually is recommended for you to take it right after 189. But again, because you've taken Data 100 and Data 100 gave you like 40% of 189, you could probably directly get into 182 as long as you're like solid on the math and linear algebra piece of things. I personally like 188 as well. 188 is a good kind of survey course if you're interested in just getting kind of a flavor of different flavors of different subfields of AI. It talks a little bit about neural network. It has a little bit of reinforcement learning. It has some lectures on local search. So it's kind of giving you an overall idea of what are different algorithms or sub areas in the entire umbrella of AI. So if you just want to take one course and a general course, 188 is a really good course for you to take. I said 102 is like a natural course also after Data 100. It's a little bit math heavy because it goes over causal inference. It has the statistics, but it also has neural network as well. So if that's the only thing that you want to get, 102 might also be a good option. CS 127 is also a great course. It thinks about ML from the optimization perspective. So different types of optimization. So for example, here in Data 100, you've seen that we're doing gradient descent in order to optimize the model. You'll see a whole lot of different types of optimization techniques and the math behind it in X 127. If those are the things that you're interested in, that's a good course. We also have some grad courses that you might be able to get in or audit. We have reinforcement learning course, which is a great course. And then we have also 288, our natural language processing course. We don't have, I think, an undergrad NLP course yet, but I've heard Info 159 can also be a good option that you can take. All right. If you want to learn more about the courses, enrollment, who's teaching, if there's going to be an additional sections being added, if there's going to be like expansion to the wait list or the class or whatever, not X, Ed Data 001 is going to be your friend. So the link is on the slides. Sign up, and then all the faculty and also the advisors are there. And then we should be able to respond to any enrollment-related questions that you have about data science piece of things there as well. So with that, the next thing that you want to talk about or think about is like, how do you do kind of self-learning? What do you do over summer? If you have internships, that's good. If you don't have internships, you might want to prioritize what you're going to do in the summer and do a little bit of self-study and do like personal projects if you want. One thing that I said to all of the students in the office hour, for those who came to my office hour, is that one great thing about the way that courses at Berkeley are scheduled or structured is all of the great recordings and course notes and textbooks. So you can self-study on a lot of these courses that I listed, and a lot of these ML courses do have online resources. Do study them. There is also great kind of online tutorials towards data science is also great. Feel free to read all of these online blogs. There's a lot of good blogs online that you can learn, that you can read, and the online videos that you can watch in order to learn neural network, deep neural network, and different things that would excite you. If you're looking for data sets, there are some good data sets on GitHub. There's Kaggle, and there's also Google's data set search engine that you can use in order to search for like what flavor of data set that you're interested in. Kaggle has its own competition, so the task is defined, or like when they release a data set, they will also kind of have a task or objective tagged to the data set. So if you want more structured kind of project, you might want to go to Kaggle and search some more on there. We also have Data 104 that we recommend that all of the students take, and it's actually a requirement for data science major. So this is where we are asking you to make sure that as you're working on these projects, use your power wisely. You might think that you're just a beginner in the data science field, but you actually are not. You learn so much in Data 100 and throughout all of the courses so far in data science. And this is a good time for you to think about your power and how you want to incorporate ethics in all of the projects that you're doing. So last piece. This course was one of the largest offerings of Data 100, and it was not possible without the great work of all of your TAs. So we have two of your head TAs here, Shiny and Mir. Great shout out to them that they manage our entire course stuff. So this was the largest course of staff that we have had since the beginning of Data 100. I think we have close to 70 course of staff in the on the staff actually hired, and it was a great work for them to basically manage this this team. We also had leads for different areas. We had leads for logistics, content, infrastructure, data scholars. Anything that happened had a lead in Data 100. Joy and I would not possibly be able to manage all of the aspects of the course. So great shout out to all of them. And I want to thank all of them again. We also had some great UCS2s that you had seen in discussions. So you might see some familiar faces. We got glowing reviews of our UCS2s. So we're so happy that we were able to recruit them for the spring, and we're hoping that we can also recruit them also for the fall. This is so exciting. They contributed a lot to different aspects of the course. We also had UCS1s in the team. So UCS1s responded to all of your questions on Ed before we had Edison, and also now reviewing Edison's responses as well. They held office hours and they also graded your work. And they were also integrated in part of the other teams that we had for testing your homeworks, for resolving infrastructure issues that you also had. They were also in training so that later on they can also become UCS2s. So we have their names and their pictures here, and their pictures and names are also on the website. So you can see that we had a very large staff, and we're so excited about all of their contributions. The spring 2024 was the second largest offering of Data 100. Close to 1,200 students across all of the sections were enrolled in the course, and these large courses are not possible without the great TAs that we have. So I would like to ask all of you to fill out the ASC application when it opens up if you're interested in joining the course staff for Data 100 for any other course, and contribute to the teaching mission of the data science department so that we can keep offering these courses at the quality that we do. With that, it was a pleasure teaching this course. Thank you so much for being such a great set of students in Data 100. We're so excited for what this course is going to take you in the future, and we're so proud of how far you have come so far in the data science journey. Thank you and goodbye.